In this lecture, we're going to be looking at Hellenistic mathematics. The last lecture ended with Euclid of Alexandria sometime early in the 3rd century BC. We're going to pick up there and continue right through until 400 AD. This lecture and the next lecture are going to be separated. In the next lecture, I want to put all of the work on astronomy. And so this lecture is going to focus on 700 years of Hellenistic mathematics, but without any mention of the astronomical work that would be done. As I mentioned in the last lecture, it was Ptolemy I who established the Museum in Alexandria, in what today is Egypt. And this would become a center for mathematical work actually for the next 700 years. Aside from Ujjain in India, there probably is no other place on Earth that has been a center of important mathematical activity for such a long stretch of time. Ptolemy's successor, Ptolemy II, would go on to build a great library that would be there to support the museum. And his successor, Ptolemy III, then would make a point of really building that library up into the greatest repository of books anywhere in the world. And in fact, there are many stories of people being pressed into loaning copies of their manuscripts so that they could be recopied. Anyone who traveled to Alexandria and was taking a book, a scroll with them, was required to loan this scroll to the library. And sometimes, if it was a very valuable scroll, the scroll would not be returned to the person that it was taken from. Rather, they would have to leave with a copy of the book that they arrived with. We also know that Ptolemy III did get in contact with many other of the rulers of the Eastern Mediterranean and aggressively went after books from other sources. One of the first mathematicians to follow Euclid in the Museum was Eratosthenes, originally from Cyrene. Born around 276 BC, he would die around 194 BC. In addition to being a mathematician, he was the third librarian of the great library in Alexandria. And he did a number of very interesting mathematical accomplishments, one of which is to find a general method for finding all of the primes below a given number. So, for example, if you want a list of all of the primes less than 1 million, there are about 78,000 of them. There is an algorithm or procedure that Eratosthenes came up with called the sieve of Eratosthenes, which is a method of generating all of the primes. And even today with our powerful computers, the kind of procedure that these computers use in order to find all of the primes below a given number, such as the primes less than 1 million, rely on the idea behind Eratosthenes' sieve. Something else that Eratosthenes accomplished was to measure the circumference of the Earth. Now, it was known in ancient times that, in fact, the Earth is round. It's a common myth that people right up into the Middle Ages believed that the Earth was flat. In fact, they were quite aware of the fact that it was round. One of the arguments for knowing that it was round is the fact that as a ship sails out to sea, you see the bottom of the ship disappear first, and the mast is the last part of the ship to disappear because it's disappearing over the curve of the horizon. But there's an even more immediate way of seeing that the Earth must be round, and that's by looking at a lunar eclipse. A lunar eclipse happens when the Earth comes between the sun and the moon, and so the shadow of the Earth is projected onto the moon, and you only have to look at that shadow to see that it's round. The Earth has to be round. And if it is round, then the question comes up, how large is the Earth? And this is a question that Eratosthenes wrestled with, and he came up with a very ingenious way of figuring it out. It's known that the sun is so far away from the Earth that the rays of the sun hit the Earth essentially as parallel lines. And so what you can do is find a place where the sun is directly overhead at a certain time of year, and then find another place a certain distance north of that, and figure out the angle that the sun's ray makes at that northernmost point, at that more northern point, and compare that angle to figure out that distance, what angle of the total circumference of the Earth is being measured here, and use that to extrapolate the circumference of the Earth. Eratosthenes actually did this. What he did was to dig wells, one in southern Egypt and another one near Alexandria. He chose a time when the sun was directly above the well in southern Egypt and looked at the shadow, the angle that the sun made with the well near Alexandria. He was very lucky in being able to accurately measure the distance between the two wells and came up with a measurement of the circumference of the Earth that essentially is right on. He came up with something between 24 and 25,000 miles, or the equivalent in the units of that time, of something between 24 and 25,000 miles, which is what the circumference of the Earth actually is. One of the problems, of course, is that there were lots of people who were estimating the circumference of the Earth at this time. Eratosthenes' estimate was one of many estimates that were out there, and an independent observer didn't have any good way of knowing which one was correct. It wouldn't be known until much later that, in fact, Eratosthenes had been correct. I want to spend most of my time in this lecture at looking at one of the friends and colleagues and contemporaries of Eratosthenes. This is Archimedes of Syracuse, certainly the greatest of all of the mathematicians of the Greek world. He was born around 287 BC, died in 212. He was noted as an engineer. He is credited with inventing the hydraulic screw. We know that he went to Egypt, that he did spend some time in Alexandria, and the tradition there is that he invented the hydraulic screw. So this is a screw mechanism that can be used to lift water, and he invented it for use in Egypt. He probably did not invent the block and tackle, but he certainly understood the principles behind the block and tackle and was very instrumental in developing this idea. He also discovered the power of levers, and he is famous for his quote, "Give me a place to stand and I will move the earth." If you've got a fulcrum point and you've got a long enough lever, somebody who is as puny as a mere human being actually is capable of moving an object as large as the earth through the mechanical advantage of using a lever. Archimedes also turned his attention to vehicles, to machines of war, catapults in particular. Burning mirrors are something that he is credited with inventing. Certainly Archimedes was very much involved with optics, with the properties of mirrors. The tradition is that in 214, when Marcellus, the Roman general, was attacking Syracuse, one of the defenses of the city that Archimedes came up with was to line up soldiers with polished mirrors that he would focus on the ships and set them ablaze. Almost certainly this didn't happen, and an interesting item of debate today is whether this is even possible. Some people argue that it is not possible. Others argue that if he got things just right, there are ways in which he might have been able to succeed. But one of the important points is that Archimedes was well known to the Romans as somebody who was extremely inventive. And it is said that the Roman soldiers were so terrified of these engines of war that Archimedes was inventing that all the defenders of Syracuse had to do was to drape a little piece of rope over the parapet, and the Roman soldiers would assume that Archimedes was about to unleash some terrible new weapon, and they would flee in terror. The Romans would eventually conquer Syracuse in 212. And it was again the Roman general Marcellus who was leading the Romans when they did conquer Syracuse. Marcellus was well aware of Archimedes, and he greatly valued the contributions that Archimedes was making, even if he was working for the people in Syracuse who were his enemy. And the story is that Marcellus sent one of the soldiers to go and find Archimedes and bring him safely back to the Roman camp. and that the Roman soldier misunderstood the order, simply that he was supposed to bring Archimedes back. And the story is told that the soldier came to the house of Archimedes, general chaos going on in the streets around him as the soldiers were entering the city and pillaging and burning the city. And the soldier came up and he discovered Archimedes deep in a mathematical piece of work. Archimedes, and there is a mosaic that shows this, Archimedes was doing his calculations on a sandboard, which is probably the way he really was doing calculations at that time. So you wouldn't want to waste valuable papyrus or other writing surface in order to put something indelible if you were just doing mathematical calculations. So you would write them with your finger on a board that was covered with fine sand, and once you found your answer, then you could wipe it out and reuse the sandboard again. And so the soldier finds Archimedes deep in his mathematical calculations. He orders him to follow him. Archimedes says, "No, let me finish these calculations first." And the soldier, who believes that he must get Archimedes back without delay, kills him on the spot, rather unfortunately. And so that is the death of Archimedes. I've described Archimedes as a great engineer, and certainly that is where he made much of his reputation at the time. But he has also left a very important mathematical legacy. And in fact, we've got an indication that it was the mathematics that was most important to Archimedes, because Archimedes had asked that on his tomb there be erected a sphere contained within a cylinder. And this refers to Archimedes' calculation of the volume of a sphere, which he considered to be his greatest work. And in fact, we do have independent confirmation. Cicero visited Syracuse in the year 75 BC, and he found the cemetery where Archimedes was supposed to be buried, and in fact, he did find this tomb of a sphere inside a cylinder. The result that Archimedes found is not the usual way we have of stating the formula for the volume of a sphere. We remember that formula, if you've been taught it in grade school, as 4/3 pi r cubed. So 4/3 times pi times the cube of the radius. The way Archimedes stated this was that the volume of the sphere is 2/3 the volume of the cylinder. So if we put a sphere inside a cylinder so that the circumference of the sphere exactly matches up with the circumference of the cylinder, and the height of the sphere is equal to the height of the cylinder, it's easy to work out the volume of the cylinder. The volume of the cylinder is the area of the base, which is pi r squared, times the height of the cylinder, which is the diameter of the sphere, which is 2 times r. So you take the base, pi r squared, times 2r, and you get 2 pi r cubed for the volume of the cylinder. If the sphere is 2/3 the volume of the cylinder, then the sphere is 2/3 times 2 pi r cubed, which is 4/3 pi r cubed. But the way the ancients thought about the volume of the sphere is that it was 2/3 the volume of the cylinder. Archimedes worked this out. He worked it out using the method of Eudoxus of Cnidus, this method of exhaustion that Euclid had talked about, taking this volume and breaking it down into thin slices. You can find the volume of each of the thin slices and then approximate the volume of the entire sphere by adding up the volumes of the thin slices and seeing what that number approaches as you take progressively thinner slices of the sphere. This is the idea behind integral calculus. Integral calculus, really at its heart, has the problem of finding areas and volumes, and it works by precisely this kind of slicing mechanism that was first introduced by Eudoxus, later developed by Euclid, and really perfected by Archimedes. And it's not too much of a stretch to say that Archimedes understood integral calculus. Now, when we get to the 17th century, we will see that all of calculus involves much more than being able to find areas and volumes. But this basic idea is something that Archimedes really understood. Something else that he was able to do is to find a way of approximating pi essentially to arbitrarily high accuracy. So remember that pi is the number of times that the diameter of a circle is used to measure off the circumference of a circle. The diameter goes around the circumference 3 and a little bit, and the number of times the diameter goes around the circumference is this number we refer to as pi. Incidentally, the use of that particular letter, the Greek letter P, for perimetros is something that would be introduced in the 18th century of the modern era. Before then, people did not use this Greek letter pi to represent the ratio of the circumference to the diameter of a circle. But nevertheless, people were interested in this ratio. And Archimedes began by considering a hexagon, a six-sided figure, that fits precisely into a circle. And if I've got a hexagon, a six-sided figure, it's made up of 6 equilateral triangles. And that means that the circumference of the hexagon is 6 times the radius of the circle, or in other words, it is 3 times the diameter. If I start out with a 6-sided figure, a regular hexagon, in my circle, its circumference is going to be exactly 3. And what Archimedes succeeded in doing is figuring out if I've got a polygon that sits inside a circle, a regular polygon, all of the sides have the same length. He figured out how to take that polygon and double the number of sides and find the relationship between the new circumference and the old circumference. So once he knew that a hexagon inside this circle has a circumference of exactly 3, he was able to work out the circumference of a 12-sided regular polygon. And from there to 24 sides, and from there to 48 sides, and from there to 96 sides, and he was able to measure pi accurately to about 3 digits. About 3.14 comes out of recognizing that pi can be approximated with this 96-sided regular polygon. Archimedes could have gone further with that, but he chose to stop at that point. The next mathematician I want to talk about is Apollonius of Perga, born sometime around 260 BC. And the big contribution that I'm going to talk about today from Apollonius is his work on conic sections. As I mentioned in the last lecture, we know that Euclid wrote a book on conic sections, but we don't know what he said about them. And all of our evidence of what was developed in Hellenistic times about conic sections comes from Apollonius. Incidentally, we're going to encounter Apollonius again in the next lecture because he also has important contributions that he made to astronomy. But what he was looking at is conic sections. So these are curves that can be obtained by slicing a pair of cones. So I take a pair of cones that meet point to point, and I consider what happens as I slice through these cones. If I make a horizontal slice through one of the cones, I'm going to get a circle. If I tip that plane that slices through the cone slightly, it's going to elongate my circle, and I'm going to get an ellipse. So a circle that's simply elongated along the axis in the direction in which I'm slicing by this plane. As I move the plane up to an ever steeper angle, my ellipse gets longer and longer and longer, until finally I take a plane which is actually parallel to one of the sides of the cone, so that the plane comes in, hits the cone, and then never leaves. And what happens is that my ellipse stretches out so far, and then suddenly it opens up at one end, and I get a parabola. If I now continue tipping that slicing plane, if I tip it just a little bit more, it's now going to intersect the other cone. And as it intersects the other cone, I'm going to get 2 pieces. I'm going to get one piece on the bottom cone and another piece on the upper cone, and those 2 pieces together give us the curve that is called a hyperbola. And so we've got the circle, the ellipse, the parabola, the hyperbola, All of these basic curves are united in this idea of slicing cones. And what Apollonius of Perga is able to do is to explain properties of these conic sections, these various curves that are all related in this way, and find the things that are common among them. Apollonius's work on conic sections would eventually become an important part of analytic geometry, when geometry and algebra get merged in the 17th century. And today, when we study these conic sections, we usually think about them algebraically. It makes it much, much easier to understand conic sections if you think about them algebraically. Apollonius did not have this kind of algebraic representation at hand. He had to think of them purely geometrically, and it's incredible how much he was able to do. We know that Isaac Newton, as he was writing the mathematical principles of natural philosophy, explaining the motion of the planets around the sun, he needed to use conic sections because, as was discovered by Kepler, the planets move in conic sections. They move in ellipses or parabolas or hyperbolas. And we know that Newton directly drew on this work of Apollonius of Perga in order to do his work in the mathematical principles of natural philosophy in the late 17th century of the modern era. Another important mathematician of this time, now jumping ahead several hundred years because I'm going to jump over some important astronomers who will figure in the next lecture. The next mathematician I want to look at is Diophantus of Alexandria, born sometime around 200 AD, died about 284 AD, certainly a mathematician in Alexandria of the 3rd century AD. A number of important innovations that come to us from Diophantus. He is the first person known to use a single letter to stand in for an unknown quantity. So today in algebra we use x all the time, or t, or some other letter to represent the unknown. It was Diophantus of Alexandria who, so far as we know, was the first person to come up with this idea. That does not mean that he invented algebra. As we'll see, especially when we get to the lecture on Islamic mathematics, there is much more to algebra than just having a single letter that represents an unknown, or even working with things like quadratic polynomials, which we saw that the Babylonians were able to do. But Diophantus did help set the stage for the later development of algebra. He was very well known to the Islamic mathematicians. He is responsible for a very compact notation to represent quadratic polynomials, so polynomials that involve the unknown squared plus a linear term plus a constant. Also cubic polynomials Diophantus studied, so these are polynomials that go up to a cubed term, something raised to the 3rd power. And Diophantus of Alexandria is best known for his book, Arithmetica, in which he studies problems where he is only looking for solutions that only involve integers, what today we call Diophantine equations in honor of Diophantus. And a classic example of this are the Pythagorean triples that I talked about in connection with Babylonian mathematics. So you've got an equation like x squared plus y squared equals z squared. You can let x and y be any positive numbers, and there will be a positive value for z. But the more interesting question is, can you find integers for x and y that lead to an integer value for z? So examples like 3, 4, 5, 5, 12, 13, and so on. And it was Diophantus who studied this question. And Diophantus is the first person who actually recorded a method for generating arbitrarily many of these, in fact, all of the possible Pythagorean triples. Now, going back to the Babylonian work from almost 2000 BC, we have seen that they were able to generate literally dozens of these Pythagorean triples. They probably knew the method that Diophantus explained in the 3rd century AD, but nobody actually wrote it down until we got to Diophantus. The last mathematician that I want to talk about is the first woman to appear in the history of mathematics, and that is Hypatia of Alexandria. She was born around 370 AD. We know quite precisely when she died. She died in 415 AD. She was not alone in being a woman who was doing mathematics. We do have accounts of the mathematical community surrounding the Museum at this time in Alexandria, toward the end of the 4th century AD. And we know that the Museum itself was made up of a group of scholars, and many people would come from around the Hellenistic world in order to study mathematics, study mechanics, study optics, study the other sciences there at the Museum with these great scholars. The great scholars, incidentally, so far as we know, were not paid, but they were fed. And that was good enough to get them all to come together. And we also know that the Museum had a number of lecture halls where the members of the Museum could lecture about their topic. So people would come, they would listen to these lectures, they probably would pay the scholars independently for further lessons. And there was a group of people who gathered around the Museum who would also offer private tutoring or other lessons in mathematics. And Hypatia was one of them. She was actually the daughter of a member of the Museum, Theon of Alexandria. She was quite accomplished. We know that while there is no original mathematics that is directly attributable to Hypatia, we know that she wrote commentaries on the work of Archimedes, the work of Ptolemy, the astronomer, who I'll be talking about in the next lecture. She wrote commentary on the work of Diophantus. And in fact, just recently we discovered a work that is believed to have come from Hypatia. In 1968, there was an Arabic translation of commentaries written on Diophantus's Arithmetica, and it is generally believed from looking at the contextual evidence that these commentaries that were rediscovered in 1968 probably were written by Hypatia. And so if there was no original mathematics, and sometimes that's hard to tell because the commentaries often would elaborate on the mathematical themes and develop them further. Certainly she was someone who understood the classic texts so well that she could write commentaries that would be used for hundreds, in fact, well over 1,000 years later. It's under Hypatia that the Museum comes to an end, and we do not know the exact date or the exact circumstances, but the last references to the Museum occur in the late 4th century, and they probably coincide with an event that happened in 391 AD. That's the year in which the Roman Emperor Theodosius I, who was a Christian emperor, banned all of the pagan temples. He ordered all pagan temples to be closed throughout the Roman Empire. The Museum was a center for scholarship, but remember that it was founded as a temple to the Muses, and as such it fell under this ban of Theodosius I. And so almost certainly at this point the Museum is suppressed, and the scholars who would have gathered in this temple to the Muses were disbanded. Hypatia continued to live in Alexandria and to work in Alexandria, but the coming of the Christians to Alexandria would really mark an end to this great period of mathematical achievement. 415 AD, there is a great political fight between two leaders. On the one hand, we have Orestes, who was the prefect of Alexandria, the emperor's right-hand man running Alexandria. And on the other side, we have Cyril, who was bishop of Alexandria, the leader of the Christians in Alexandria. And since the emperor himself was a Christian, to be the bishop of Alexandria was to have a great deal of power. And Cyril and Orestes were engaged in a battle to see who could really control the city of Alexandria, and with control of the city of Alexandria would really come control of Egypt. And we know that Hypatia was a strong supporter of Orestes against the Christian bishop Cyril. And in the year 415, She was walking through the city of Alexandria when a Christian mob spotted her and attacked her, and she was literally torn to pieces. And that marks the last of the great Hellenistic mathematicians, and really the end of the Hellenistic period in mathematics. We're going to be looking at the development of astronomy in the Hellenistic world, and then in the following lecture we're going to move to India, South Asia, and we're going to see how they were able to pick up the Hellenistic tradition and further develop it.